The next few videos are going to talk about the capacitance voltage characteristics of the MOS capacitor. Since it's a capacitor, we want to know how the capacitance will change as we change the voltage that we apply across that MOS capacitor. So just to ease the discussion, note that capacitance can be defined as the rate of change of the charge with respect to the rate of change of the voltage. So let's look at a few different cases. So first of all, accumulation. Okay, so here's our energy band diagram of the MOS capacitor in accumulation, and over on the right this is showing the charge distribution. So in this case it's a p-type semiconductor, so we're putting a negative voltage on the metal, and that means there's a bunch of negative charge building up on the metal. That means that there's positive charges building up in the semiconductor oxide interface, because this negative charge is attracting the majority holes here. And there is this dq prime amounts. That just represents if we're changing the voltage that we're applying to this MOS capacitor by a little bit, by dV, then that corresponds to the amount of change in charge, dq, that will be in the metal and in the semiconductor. And it's the same amount, because if we add some charge to the metal, we should add the same amount of charge to the semiconductor. Okay, so we can look at this case as just like a parallel plate capacitor and write down the capacitance. This is all capacitance per unit area. So that's C prime. The ACC is for accumulation. And so that's just equal to the capacitance of the oxide, because we have some charge building up here on the metal and some charge building up in the semiconductor. So just like a parallel plate. And the separation between the two parallel plates is the thickness of the oxide, Tox. And in your parallel plate capacitor equation you should have an A over here, but we're normalizing by area, so that goes away.